Welcome. Today, we're bypassing the high-level abstractions to explore the foundational techniques of low-level systems programming. We will dissect the mechanisms that govern memory, data access, and kernel interaction. This is not about using an API, it's about understanding the machine-level realities that make those APIs possible. Prepare for a detailed look at memory management, advanced. Our journey today is structured around three pillars of system programming. First, we'll peel back the layers of virtual memory, moving beyond the concept to the implementation details like page tables and the translation look-aside buffer. Next, we'll scrutinize dynamic memory, specifically the performance trade-offs of standard allocators and the rationale for building custom allocators. We will then dive deep into the power and peril of advanced pointer techniques, including aliasing rules that can mystify even seasoned developers. Finally, we'll demystify the system call, the explicit boundary crossing from user space to the kernel. Let's begin. Every process operates under the illusion of possessing a vast private address space. This illusion is orchestrated by the Memory Management Unit, or MMU, in concert with the OS. When a virtual address is accessed, the MMU attempts to translate it to a physical address. It first checks a high-speed cache, the translation look-aside buffer, or TLB. A TLB hit is fast. A TLB miss is expensive, forcing a page walk, a multi-level traversal of the process's page table structure in main memory to find the physical frame mapping. A page fault occurs if the mapping doesn't exist or permissions are violated, trapping into the kernel. Understanding TLB locality is paramount for performance. We all know pointer basics. Let's talk about something that bites experts: the strict aliasing rule. C and C++ compilers assume that pointers of different types do not point to the same memory location. This assumption allows for aggressive optimizations. For example, if you write to an int object, the compiler assumes no float object in the same scope could possibly have been affected. If you violate this rule, typically by type punning a pointer and accessing the data, you invoke undefined behavior. The code might work, it might crash, or it might silently corrupt data. The only safe way to inspect raw memory representation is via char-op or unsigned char-op, which are the exceptions to the rule. We all know pointer basics. Let's talk about something that bites experts: the strict aliasing rule. C and C++ compilers assume that pointers of different types do not point to the same memory location. This assumption allows for aggressive optimizations. For example, if you write to an int object, the compiler assumes no float object in the same scope could possibly have been affected. If you violate this rule, typically by type punning a pointer and accessing the data, you invoke undefined behavior. The code might work, it might crash, or it might silently corrupt data. The only safe way to inspect raw memory representation is via char-op or unsigned char-op, which are the exceptions to the rule. Function pointers are more than just callbacks. They are the C-level mechanism for implementing dynamic dispatch. In object-oriented languages like C++, this is abstracted away, but under the hood, polymorphism is often implemented using a virtual method table, or vtable. A vtable is essentially an array of function pointers. Each object of a class with virtual methods contains a hidden pointer, the vptr, which points to the vtable for its class. When you make a virtual function call, the program follows the object's vptr to the vtable and then calls the function at the correct offset in that table. This is how baseptr.draw can call the correct draw method for a circle or a square at runtime. A process cannot directly access hardware or manipulate kernel data structures. To perform privileged operations, it must request the kernel to act on its behalf. This request is a system call. Executing a syscall instruction triggers a software interrupt or trap. This causes an immediate privilege level change from user mode to kernel mode. The CPU then uses the system call number, passed in a specific register, as an index into the kernel's system call dispatch table. This table contains pointers to the kernel functions that implement system calls like read, write, or fork. After the kernel function completes, it executes a special return instruction, like sysret, which transitions the CPU back to user mode, and execution resumes. The mmap system call is a perfect synthesis of our topics. It instructs the kernel to map a file or device directly into the process's virtual address space. Instead of using read and write, you can simply manipulate the memory through a pointer. The kernel handles the page faults behind the scenes to bring file data into physical memory on demand. This avoids redundant data copies from the kernel's page cache to the user's buffer, a significant performance win. It uses pointers for access. It directly manipulates the process's virtual memory layout via page tables, and it is, of course, a quintessential system call. Mastering these techniques is a double-edged sword. On the performance side, understanding memory hierarchy, from registers to TLB to RAM, is crucial. Custom allocators can eliminate lock contention and improve cache locality. Zero-copy I/O with mmap can drastically increase throughput. However, the security risks are immense. A single miscalculation in pointer arithmetic can lead to a buffer overflow, the classic attack vector. Improper handling of dynamically allocated memory leads to use after free or double free vulnerabilities. These aren't just bugs, they are footholds for attackers to achieve arbitrary code execution. With great power comes great responsibility. We've journeyed deep into the core of system programming. We confirmed that virtual memory isn't magic, but a complex dance between the OS and MMU. We've seen that dynamic memory allocation is a field of performance engineering in itself. We've respected the power and precision required for advanced pointer use, and we have demystified the system call as the formal handshake with the kernel. The key takeaway is this: abstraction is a luxury,